Hello, dear students. Welcome on this video lecture. This is the last video lecture related to the chapter errors and measurements. In the previous video, you have learned errors in detail. In this video, we will be having a couple of numerical problems related to errors. So before we go to these problems, let's recap the important points that you learned in the previous video. That's called error. So we talked about that whenever we take any experiment, we repeat that experiment couple of times so that we have a lot of observations. These lot of observations are done in order to find out proper values or remove or minimize a random error. So let's say a physical quantity is A and that is being measured by several observations like this. Let's say there are n number of observations it has been used for. So then we will be finding out the value of that physical quantity. We call that as a mean value rather. So this mean value is equal to summation of all the observed value divided by total number of observations. So this I runs from 1 to n number. So that's called mean value. We calculate the mean value. Once we have calculated the mean value, then we calculate absolute error. So next term that you learned was absolute error. Absolute error is corresponding to each observation. So let's say corresponding to first observation, we will writing as a delta A1. It is written as a mod. It's a magnitude. That's a positive value we talk about. And its value is A mean that we have calculated over there minus actual observed value of A1. Similarly, we can find out the absolute error in second observation, third observation, and observation. Based on this, we defined a quantity called mean absolute error. Mean absolute error. So you learned about this mean absolute error. So this mean absolute error, let's say we are representing by delta A mean. So this is summation of all these delta AIs, or we can write A mean that we have calculated earlier minus AI, and this I runs again from 1 to n divided by n. Basically we are finding out the mean value of absolute errors. So that's a delta A mean. Then you have learned about quantity called relative error. Relative error. So how to get the relative error? It is defined as again plus minus. We are going to place here plus minus so that we will be writing the error, and it's going to be these mean absolute error divided by mean value. So if I can write it as delta A mean divided by delta A, or rather A, downside is A on the denominator. So delta A is indicating mean absolute error, whereas A is indicating the mean value, or you can call it as A mean. So it's representing the mean value. So that's called relative error. And then we have learned about percentage error. So what is a percentage error? You must be remembering we will be writing the same value but multiplying it by 100. So mean error, or this mean absolute error divided by mean value into 100. So that's become percentage error. So these are the quantities or terminologies that we learned in the previous video related to error. Now we will be using these properties or terminologies to solve the questions. The last point that we learned in the previous video was the propagation of error. So let's say we are having one quantity A. So we know that quantity is represented as A plus minus delta A, then B plus minus delta B. Then in addition and subtraction, we have talked about for summation and difference. In these two cases, we write delta x, that means Error in summation is delta A plus delta B. I'm writing in short, everything is in your notes, you can see from there. In case of multiplication and division, we use this relative error is equal to relative error or sum of the relative error of the participant physical quantities for the two numbers. If there are the three numbers we are multiplying or dividing, we will be writing this. Then you have seen the power formula. In case of power formula, the power comes in front of these expressions. Okay, so this was just a recap of the previous video. Now let's see couple of questions on this particular concept. So here is the first example or question, whatever you call it. I'm calling it the example. So this is the first. What you can do, you can pause this particular time and solve it. Once you solve it, then you come back and see your solution and compare it with this. Now I'm solving here. So it says the length and the breadth of a rectangular lamina is given to us this. So length is given in this format. Now you can think of why this format is given or what does that mean. It says the length is read to be as 2.6 centimeter, whereas there is an error involved as 0.1 centimeter. This plus minus and along with this is trying to say error in measurement of length. Similarly, breadth is given as this, so we can read this number properly. Now it's asking for finding the area of lamina up to appropriate significant figures, stating the error limits. So let's try to solve how we can solve this. So solution can be as this. Now since we need to find the area of a rectangular lamina, this is a very simple formula that we are supposed to use over here. I'm writing directly. Area of rectangular structure geometry is length and width. So that means we are going to operate multiplication for this purpose. So when we multiply, then this will be equal to, when we are finding the number or value of A, we will be using the value of L. Which is the value of L? This is the value of L. That means we are going to use 2.6. That's the value of L. And then we multiply this with the value of B. What is the value or reading of B? It is 1.8. So 2.6 into 1.8, this we are going to multiply. Mind it, when we are using this formula, we will write the value of L and value of B. We are not going to use the error involved in L and B. Calculation of error will be done separately. Okay, now we can multiply these two numbers and see what the number we are getting. So this will be equal to 4.68 and the unit is centimeter, so it will become square of centimeter, or you can call it as a centimeter square. So this is the value of A, but we need to give our answer in appropriate significant figures with the error limit. So that means next thing that we need to find, that is delta A. Now here we need to use the concepts that we have learned in this particular topic. Now if this A is written as L into B, so there is a product going on or multiplication going on. So in case of multiplication, the error is written as delta A upon A is equal to delta L upon L plus delta B upon B. So this is how we are going to calculate the value of delta A, that is error in area. So error in area divided by area, that's called a relative error, or fractional error is going to be equal to sum of the fractional errors in the involved physical quantities. Now what the delta L value will be? This value will be delta L, this value will be delta B. So we will be using the delta L, L, delta B, B and A to find out area or error in area. So let's write delta A. Delta A is 0.1 divided by L. L is given as 2.6 plus delta B value is 0.2 and B value is 1.8. Now again, this is a numerical expression. We can simplify it to uh, proper calculations. So let's simplify this. So after calculation, you will find it comes out to be 0.149. So this is the value of delta A by A. So it will have no unit and its value is 0.149. If it is asking about find the fractional error in area, so this will become our answer of fractional error. If it is asking percentage error in area, we simply will multiply this by 100. That means 14.9% will be our answer. But here it is asking about area. That means we need to further simplify it to find the value of delta A. So delta A is going to be equal to this 0.149 into A. Into A, that means value of A we need to multiply with. And what is the value of A? We have calculated already what the value of A is. It's 4.68. So 4.68 is the value of this A or that's area. It is in centimeter square. Again, we can multiply these two numbers to get our answer. So this multiplication goes to 0.697 centimeter square. So this becomes the value of delta A. Now after getting the value of A from here, let me mark this. After getting the value of A from here and value of delta A from here, we need to write our answer in the appropriate significant figures. Now this lamina's dimensions are being measured as length and width, and the length and width, they are measured up to 1 decimal point, or we can say up to this error in L. Error in L has one significant figure, error in B has one significant figure. Hence error in A should also have one significant figure. So that means we need to rewrite this in the appropriate number of significant figure. So the significant figure up to which this area has to, or the error in area has to be written is equal to the significant figures involved in the errors of the quantities that are there. So both are having for one significant figure. So we will be rounding off this expression to one significant figure. Now if we want to round off it to one significant figure, that means this is the only digit or place that has to be maintained. So if we want to maintain this place, then this has to be round off. Then we will see next to this is 9, which is more than 5. So this has to be increased by 1. That means this has to be written as 0.7 centimeter square. So this is the value of error in A. Now since error in A, that means delta is written as up to 0.1 decimal space or place, then the value of A should also be changed to 1 decimal place. So now we will be writing this A up to 1 decimal place. So if we want to write this up to 1 decimal place, again we need to round off this up to this decimal place. So again this 8 is more than 5, so we will be increasing this by 1. That means A has to be written as 4.7 centimeter square. Now you will see this is the value of A, this is the value of delta A. Hence answer has to be, hence answer or area has to be written as, area has to be written as, we know whenever we write a quantity, we write in this manner, A plus minus delta A. Now A has been calculated as 4.7 and this plus minus, this has come out to be 0.7. This centimeter square becomes our answer. So here are certain points that we have used. Let me quickly revise. What we have done, we have used this product rule to find the area. So first we are going to find the demanded quantity using the formulas or the concept that we know, and we will simplifying it to the numbers, and we will get it here, its value. Then we will be using the relation to find out the error. In case of product, this is the rule that we apply, you know that we have learned. Then once we have applied this rule, we will be simplifying, finding the value of change in that quantity in that way. Once we have calculated these two numbers, then we will be observing the involved quantities have errors in them, and what are the significant figures or number of significant figures in those errors. Then we will be representing our error in this quantity which we are interested in up to the same number of significant figures. So we have converted it into one significant figure because delta L and delta B, they were having one significant figure. So this is one point that we have introduced in this particular example. Another point then comes in whenever we write A plus minus delta A, then both should have same number of places after decimal, right? So if they have this is the requirement, then we need to convert this A into the number of decimal places as this delta A has. This delta A has one decimal place, so this has to be converted for one decimal place. Hence I have converted this as up to one decimal place by using the round off rule. So this will become the value of A. Once we got the value of A and delta A in appropriate significant figures and up to significant points after decimals, then we can write our answer in a proper fashion. Okay, so you just check whether you solved in this way, or otherwise you just solve it, copy it, and we will be using the similar rules in other examples or questions. So let's see the next problem. Here is the next problem. So let's write example, next example. Again, you can pause the video and solve and then come back to see the solution. It says the error in measurement of diameter of a sphere is 1%. The percentage error in the measurement of its volume is, so diameter error is given to us, we need to find the error in volume, and it is a spherical body. So that means we need to write the volume of a sphere in terms of diameter. So what the volume of a spherical object is, we know it's a 4/3 pi r for radius, right? So pi r cube. Now this is radius. If we want, we can convert it into diameter, because we know radius is equal to diameter by 2. Let's d for diameter. So this volume will become, if we go for d by 2, so this will become, I'm writing directly because it's become 8, the 6, so it becomes pi by 6 d cube. Anyway, these numbers are not going to matter for us, particularly at this example. Now, since this is the expression, now we want to write the change in or percentage error. So what we do, we will be using, like, this is d into d into d. So it will be saying delta v by v is equal to, this is a constant number. Now the constant number does not play any role. So it will become 3 times delta d by d. Now how we are getting this, let me give you idea. We have written down like a fractional error is written in case of power. Whatever the power is, that power comes in front. We had a formula. So this power of d will come in front, and the fractional error in volume is going to be 3 times fractional error in d. Once we are able to write fractional error, we can always multiply it by 100 to get the percentage error. So this will become the percentage error in volume. This is going to be equal to 3 times delta d upon d into 100. Now if we combine this together, so that's called percentage error in diameter, and this is the percentage error in volume. Now since this is the percentage error in diameter, and the percentage error in diameter is given to us as a 1%, so this number is given to us as a 1%. So this will become 3 into 1. That's how much? 3, which we can rewrite it as percentage error in volume will be equal to, 3%. Then we can see which option is matching. Options are 1, 2, 3, 4%. So we will say 3% becomes the right option. Is it making sense? So whenever we need to find the percentage error and other percentage errors are given to us, what we can do, we first will be looking after the formula that relates the quantities which are being asked and which quantities are involved. Then we will be using the error concept. From here to here we have used the error concept. Whatever the power is, that power comes in front, constant number, they do not play any role. If you remember how this came, so we used to take the log value and going using the change, that's also called differentiation. So this comes in. Once we know this, we can always multiply by 100 to get the percentage. It's like going from relative error to percentage error, hence solving then our answer. Okay, I hope you have got it. If you have got it, we can go for the next question. Okay, here is the next problem. I'm writing as exercise or example, whatever you read it. Again, you can pause and solve and then see. Now I'm solving over here. It says a physical quantity x. So x is any physical quantity that has been expressed as a square b upon c raised to power 1 by 3 under root d. This is calculated by using measured quantities a, b, c and d. So a, b, c and d are known to us. Once a, b, c and d are known to us, we can simplify it to find the value of x. So this is how some formula is being given. Now we need to talk about in terms of error. It says if the errors in measurements of a, b and c are this respectively. That means measurement of a has 1% error, measurement of b has 2% error, measurement of c has 3% error, measurement of d has 4% error. So that means measurement of d has highest amount of error, whereas the measurement of a has the least amount of error. Anyway, let's go ahead and see what the question is demanding for. It's demanding that find the percentage error in the measurement of x. That means we know what the error is in the involved quantities, and we need to find the error in this physical quantity that depends on these quantities. Okay, so again we will be using the formula of errors. So this is power and product and division. Whenever the power and product and division is, we can write it. This is given as x raised to power x is equal to a raised to power 2b upon c raised to power 1 by 3 and under root d. So we can rewrite it as x is equal to a square b upon c raised to power 1 by 3 and d raised to power 1 by 2. That's how it is written. Now we have understood what this formula of error for power expressions are. Whatever the powers are, they come in front. So delta x upon x will be equal to, I'm writing it directly, so it's going to be 2 times delta a upon a, that means error in a or this fractional error in a, plus delta b upon b. Here it was 1, so we are writing 1, plus we have also talked about whether it's in denominator or numerator, we always write a plus because errors are being added up, and this will be 1 by 3 delta c upon c, and finally plus half delta d upon d. So this is how power expressions are used. So it says fractional error in x is equal to 2 times fractional error in a plus fractional error in b plus 1 by 3 times fractional error in c plus half times fractional error in d. Now these are in the fractional terms. Now we can write in terms of percentage. So for writing in terms of percentage error, we will writing delta x upon x into 100. So that's a percentage error in x. And that's what we are looking for. This is going to be equal to 2 times delta a upon a into 100. That means what we are doing, we are simply multiplying by 100 on both the side. So this will become the percentage error of a or in a, and that value has been given us as 1, plus 1 times delta b upon b into 100. So that's a percentage error in b, plus 1 by 3 times delta C upon C into 100. That's a percentage error in C. That's a C. Similarly, 1 by 2 delta D by D into 100. Now whatever these quantities are written in bracket, they are indicating percentage error, and all these four quantities have been given to us as 1, 2, 3 and 4 respectively. So we can go ahead and we can talk about this is going to be 2 into 1% plus this is 2% plus 1 by 3 into 3%, and this is 1 by 2 into 4%. So this is in percent. So we can say percentage error in measurement of x is this number, which is coming as 2 plus 2 plus 1 plus 2, this many percent. So ultimately it becomes 2 plus 2, that's 4 plus 1, 5 plus 2, 7. That means percentage error in measurement of x is going to be 7%. That becomes our answer. So if a complicated expression is known to us or given to us like this, what we are going to do, we will be using the power expression for error. And in error, what is the power expression? Fractional error in that quantity is equal to sum of the fractional values along with the multiplication of the power. Okay, and once we are multiplying both sides by 100, so these numbers becomes percentage error. So whatever the error is given to us, we can simply write over here and we will sum them up, we will get our final answer. Mind it, whenever we are using this kind of expression, no matter whether the quantity is on the numerator or on the denominator, we always add them up, and whatever the power they carry, these powers comes in front. We should not get confused by this way. If someone would have written this expression, maybe let's say I'm writing over here, just avoid those kind of thing. This similarly this x could also be written as like a raised to power 2, b c raised to power minus 1 by 3, d raised to power minus 1 by 2. Can we write the same expression in this manner? Of course we can write that. Whenever then we will be writing this fractional error in x using the formula. So this power will come in front, 2 into delta a upon a, plus b will be written as delta b upon b, plus, now here the power seems to be minus 1 by 3. So we are not going to write as a minus 1 by 3. We will be writing the positive value of it, because we know this minus sign is simply indicating this is in the denominator, and we have already talked about whether it's a denominator or a numerator, we need to add them up. So this should not be written as a minus 1 by 3, rather we will write it as a plus 1 by 3 delta c by c, and similarly it will be written as plus 1 by 2 delta d by d. Are you getting what I'm trying to indicate? So if the powers are written in the negative terms, you simply remove that negative term and add them up, or that means without negative you put there and it should be added with the other terms. Making sense? So this is how we calculate the errors, and once you have got it, then no matter which type of question is, how many these quantities are involved, for each and every quantity you are going to do this kind of stuff. I'm hopeful you have understood it, so copy it, and if you have question or query, you can always ask. Now let's move towards the next problem. So here is the next problem. Let me write that as example. Again, you can pause the video and solve on your own, then come back to see the solution. It says, in an experiment for determining the density is written by rho later. This symbol is read as a rho, so that's a density of a rectangular metal block. A student makes the following measurements. So these are some measurements made by a student. Mass of the block has been measured as 39.3 gram. Similarly, length is measured as x, width is measured as y, and thickness has been measured as z, and they have been measured in terms of centimeter. Numerical values are given there. It further says the uncertainty is basically error in the measurement of mass is plus minus 0.1 gram. That means this is the value of delta m. So we can catch delta m value is this. And in the measurement of xyz it is plus minus 0.01 centimeter. That means this is indicating for delta x, which is also equal to delta y, which is also equal to delta z. So error values are known to us here. Find the value of density in gram per centimeter cube. That means we should not supposed to change the units. So whatever the units it carry, the same unit we need to follow. Up to appropriate number of significant figures stating the uncertainty in the value of rho. That means we need to find the error in rho and we need to find the rho value. So both rho and delta rho we need to find. So this is the question. Once you have understood the question, we can talk about the solution. So solution of this problem can be as follows. First we need to connect this density with the mass and with these dimensions. Now if there is a rectangular metal block, so can we find out what the volume it is going to carry? So volume of the block is going to be multiplication of all the dimensions like length, width and thickness. So can we say it's going to be x, y and z? That's the volume. Once we know the volume, can we write the density? Density is going to be mass divided by volume. So volume is x, y and z. Now this is again a product or multiplication formula or similar to that, or division formula. So here we need to first we need to put the value of m, x, y and z in order to find out what the value of density is. So let's place the value of x, y and z along with the value of m. So m has to be written as this value because this is the measured value. This is going to be 39.3 divided by, now we will be placing the value of x and y and z. X is 5.12 in centimeter, then the value of y which is 2.56 in centimeter, and the third, that is z, is 0.37 in centimeter. So our answer is going to be in gram per centimeter cube. Now if we simplify this number or do this calculation, we can find out what the value is going to be. So you can make this calculation and let's see what this comes out. So after calculation it comes out to be 8.1037 gram per centimeter cube. So what we have done, we have found out the value of rho. Okay, then we need to find the value of change in rho or error in rho. Since this is multiplication or division involved, so we can say since the formula is going to be fractional change in rho is going to be equal to fractional error in mass plus fractional error in length plus fractional error in width plus fractional error in thickness. Are you getting what I'm doing? You should be getting it, because this you can think of these mass and xyz, they are in division, and xyz they are in multiplication. So whether they are numerator or denominator, we all we simply find their relative or this fractional error and we sum them up. Here we can think of they are having power 1 1 1 1, hence we are multiplying them 1 by 1 1 1, which we are not writing. If there would have been power 2, that power would have come in front as a multiplication. Okay, now we got the value of delta m, this is delta m. We got the value of delta x, delta y, delta z. We got the value of x, y, z and m. So we can put all these values over here to get our answer. So let's try to put the values. Delta m will be written as 0.1 divided by m value is given as a 39.3 plus delta x value is given to us as a 0.01. When we write this value of error, we always write a positive value. 0.01 divided by the value of x, which is 5.12, plus error in y, which is 0.01 centimeter, divided by 2.56 centimeter, that's a 6, plus error in z, which is 0.01, divided by the value of z, which is 0.37. It is a bit calculation. If you do this calculation, you will find the value of this numerical expression. So the calculation reveals that the value of delta rho by rho comes out to be 0.0353. You can check the calculation. Calculation you can always do. What you need to catch from here is the idea what we are doing. So from this expression of rho, we are writing the fractional change in rho. Once we have written this, so from here we can easily find out what the value of del rho, that is error in rho, is going to be. Is going to be 0.0, there is a decimal, 353 into the value of density. We have already calculated the value of density. It's 8.1037. Again we need to multiply these two numbers to get the value of delta rho, that is error in rho. So this calculation will give you the value of delta rho, which is going to be equal to 0.286, and it will come in terms of gram per centimeter cube. Now we have calculated a lot of things. We have calculated the rho value, and the rho value came out to be this number. And here we have calculated the delta rho, that's got error, that has come out to be this number. Now we will see, we will be writing them in appropriate significant figures. So the value of delta rho, that means error in rho, has to be written in terms, or that has to be decided by looking at the values of error of the involved quantity. So delta m has a 0.1 value, whereas the delta x, delta y, delta z, they have a 0.01 value. Now if you see the significant figure for this delta m, this is one significant figure. If you look at the significant figure of these quantities, they also have a one significant figure. That means delta rho must have one significant figure. As we just discussed in last example, or some previous example, that the value or the number of significant figure in the error of this quantity is decided by the error in these quantities and the significant figures in them. So if we want to write this total number of significant figure of delta rho, then we need to check what is the significant figure for delta m, delta x, delta y, and delta z. Whatever the significant figure these quantities have, this quantity will also have the same number of significant figures. Okay, so using that point, we will say this must be represented up to one significant figure. Since we want it to be one significant figure, so it has to be written in appropriate number of significant figure as delta rho is equal to, or error is equal to 0. Now this is the decimal place up to which we need to round off. So it's going to be 2, and in front of 2 is this 8, which is more than 5, so it has to be written as a 3. So this 3 gram per centimeter cube is the density, or appropriate value of the density. Now since this has one decimal place, hence the value of this density has also be round off to one decimal place. So corresponding to this, rho we are going to write only up to one decimal place. So for one decimal place it will be 8.1, and rest we will be scrapping because this is 0, so 1 will remain 1, it will not increase because this 0 is less than 5. So this is going to be 8.1 gram per centimeter cube. Now hence we can write our answer. So how the answer has to be given? If we need to write answer of density, so it has to be written density plus minus change in density, or error in density. So it has to be written as 8.1 plus minus 0.3. That's our answer. This many gram per centimeter cube is proper answer including error in or up to appropriate significant figures. Okay, so I hope you have understood the extra 2 points that we are discussing since last couple of example. One, writing this error up to how many significant figures as the significant figures of the involved errors. Then writing the quantity, that physical quantity, up to that decimal places up to which this delta row or error has been written. Okay, so if you have understood this, that's well and good, and we can go for the next problem. Well, this is another an important example, quite popular in examination. And again, you can pause the video and solve by your own, then see the solution over here. It says the time period of a simple pendulum. This is a formula, you know, T is equal to 2 pi under root L by G. You must be knowing about this. Where L is the length of the pendulum, G is the gravity or acceleration due to gravity. The value of length has been measured as this centimeters. So that's the measurement of L. And it has been measured with the meter scale having least count this. So that's the least count. Time for 20 oscillations has been measured as this by using a stopwatch which has a least count as this. Calculated value of G. So what will be the value of Z after calculating using this expression? So these are the options, 9.87 and then 9.9, then this. So we need to find the correct option. You see all the options are very close by. So here the rules are going to be important for us. So let's say how we are going to solve this. Now we can rewrite this expression. If we want to rewrite this expression, so this can be written as, let's say we are interested in G, so we can find the G expression out of it. G expression will be equal to 4 pi square, or we can write it as, after squaring we will get like 4 pi square into L divided by T square. Now 4 pi square, we know the value of 4, we know the value of pi, we know the value of L. What is the value of L is given over here. We need to use the SI unit, so this L has to be converted into meters. So that's basically 1 meter. So L has to be placed as a 1 meter. And what the T is, so let me write over here. L has to be taken as a 1 meter. And what the time period is going to be, we can say 20 oscillations takes 40.0 second. So what the one oscillation is going to take? So you can say, right, it is a 40.0 divided by 20. So that will turn up as 2.0 second. So that's the time period. Now if we use the value of T and value of L, we place here, we know the pi square very close to 10. So from here the Z value can be calculated. So if you simplify this, put in the proper values, pi can be taken as a 3.14, and if you simplify, G comes out to be, so let me write the solved value. G comes out to be equal to 9.872 meter per second square. So that's the value of G. Now if you look at this, then we will not be able to decide yet, because we need to also find what this delta G is going to be. That means error in G. Now this is again in terms of power and multiplication. So using this, can we write what the error in G is going to be? So, or at least we can write the formula. Formula is going to be fractional change in G or fractional error in G, that is delta G by G is going to be equal to, we have talked about 4 pi square. These are the constant number, they are not going to play any role. It's going to be delta L upon L plus T has a power 2, and it will become 2 times delta T divided by T. Now we can put the value of delta L. What is the value of delta L? We can find over here 0.1 centimeter. And what is L? This is 100 centimeter, because writing in same unit will work. So it's going to be 0.1 centimeter divided by 100 centimeter plus 2 times. What is delta T? Delta T is the error in this, or you can call it as a least count. So least count is 0.1. So least count is going to behave like delta T. So 0.1 divided by T. What is the time period? We have calculated time period. Time period came out to be 2.0. Now we can simplify this expression. Okay, before we go for simplification of this, we need to recheck one point. and that point to be rechecked is this delta t. This delta t will be error in time period, but this 0.1 second that we have been given is, this is not the error in time period, rather it is the error in measurement of time, right? That means when we are measuring this these many seconds, then whatever this continuous time is in this point 0.1 second error is coming, and we are using 20 oscillations. Okay, so what we should start, better would be writing this, that let's say this is n number of oscillations that we are having, and this is the time t, then this will be behaving like delta t. So this delta t is error in t when we take 20 oscillations. Making sense? Hence we can write time period. So whatever the time period we are using, so that time period will be written as total time divided by total number of oscillations. Total time divided by total number of oscillations. Now what the difference you are going to get is, this n is having no error. That means n is error free, because this 20 oscillations are perfect 20. Okay, and error is coming on this small t. So what we should do, we should basically replace this capital T by t by small t divided by n. So this will be appropriate way to go ahead, because this delta t has small t has a 0.1 value and n is errorless. So what we are going to get it is this. So let me rewrite over here. I'm just erasing this part. This calculation which we proceeded with had a bit error in it, so we are just rectifying it. Now basically we will replace that t value over here. So if we replace that t value over here, the expression will come as it will become small t over here. I'm writing this into n square. I am modifying the same formula. So this is the modification which I have brought with this different color. So small t n divided by n, which was this capital T. So this capital T has been written over there. Now this will say, just like 4 pi square is a constant, n is also a constant. So n square is a constant. So that's not going to play any role in the error that brings the error in G. So it's going to be L that is going to bring error, that's delta L by L plus 2 times. Because of this, we need to write delta T by T in this. So this is the correction which I have made with this different color. So please note this, and then after we can go ahead. So what is happening, if there is some constant of fixed number, that's not going to play any role in the error. Error will come by those numbers or quantities measurement which counts the error. Okay, now let's put the value of delta L. We started with the delta L value, which was quite correct enough, 0.1 divided by, and then L value was 100, or we can write as 100.0 plus 2 times delta T. Now this delta small t is 0.1 divided by what the T measurement was. T measurement was 40.0 or 40.0. Now we can simplify this to get the value of delta G by G. So let's do this calculation and see what it is coming. This value after calculation comes out to be 0.006. Once we got this value, then we can go further and we can find out the value of delta G. So let me write the value of delta G in front of this. This is going to be equal to 0.006 into G value, and the G value we have already calculated as a 9.872. Now these two numbers we can multiply to get the value of delta G. This multiplication comes out to be 0.059 meter per second square. Now we got the value of delta G here. We got the value of G earlier as the calculations. we have done earlier as well. So from this expression we have written this expression, and this expression has been converted in terms of small n, t and l value. We placed all the values and did the calculation. I have not shown this calculation. You can do this calculation, put the value of pi, l, n and t, check whether you are going to get this number. That means we can think of that you can get the value of small g. Once you have got this small g value, then what we are going to do, we will convert to this. That means we will be converting it into error format. In error format, this 4 pi square n square being constant will play no role. It will be delta l by l plus 2 times delta t by t. Now we place the value of delta L, then delta T multiplied by 2, simplified this, came out to be. Then we multiplied this with G, then delta G came out to be. So this is simple calculation. Simple in the sense, as far as the concept is concerned, that's a simple and straightforward. And calculations will be a bit calculative, so you can do so. Now once we have got the value of G and delta G, then we need to represent delta G in appropriate unit, and we need to watch which is the correct option. Now if you look at this 0.059, you might get this 0.059 is over here, 0.5 is over here, this is there, so many numbers, right? So we need to go for the appropriate figures. Now you see, when we measure this delta L has a one significant figure. When we measure this delta T, this also had a one significant figure. That means delta G must also have a one significant figure. So we need to rewrite this delta G up to appropriate number of significant figures. So significant figure should be 1. Here we are having two significant figures, 9 and 5. These zeros are not counted. So that means this 9 has to be rounded off. So this has to be changed. Since this 9 is more than 5, so this will become 6. Okay. So that means the appropriate value of delta G is going to be 0.06. So meter per second square. This should be the value of small g. Once we are writing this as a small g, that means 2 decimal places we are writing it up to. Hence g must also be written up to 2 decimal places. So this is the expression of g, which was up to 3 decimal places, so it has to be rounded off. So this 2 has to be dropped because it's less than 5. So it becomes 9.87. 9.87 meter per second square. Now converting these two together, we can write our answer should be in terms of g plus minus delta g. So it should be g plus minus delta g. So if we rewrite it, it should be written as 9.87 plus minus 0.06 meter per second square. So this should be our final answer. Now check which option you are going to find it. So if you go to the first option, it's a 9.87, yes, plus minus 0.06, you say yes, that's our answer. Now you see second option is also very close, third option is also very close, fourth option is also very close. So we need to do our calculation appropriately or correctly, and we need to follow the rules correctly, right? I'm re-explaining it, and that's going to be important for us, right? So whatever the expression is given to us, we will rewrite that expression in proper format. That means in terms of the or we will be segregating that quantity which we are calculating. Then whatever the informations are given to us, we will be writing those informations. In those information, constant quantities, we will need to write in terms of constant quantities, right? So L was given to us. What we have replaced this capital T as small t by n. N is a fixed number. Delta T is given to us. T is given to us. We will place all the values and calculate the value of G. Then we have used this formula of error. Fractional error is sum of these things. Then we calculated this delta G. Then we came out to the rules. The delta G should have the same number of significant figures as delta L and delta T had. Similarly, G should have the same number of decimal places as the delta G had. So using those, we can get our answer. Okay. So this was you can say the most difficult question that can be asked in the examination, not more than that, this difficulty level, but yes, you can understand. If you have a doubt or question or query, you can always ask. Let's come to this example or question. This is entirely different question and very important one, and I'm going to solve it. You see over here, It's a different, as I said, so you just observe what's going on. You will get a formula in this question as well. So it says two resistors, one is R1, that's 100 plus minus 1 ohm, another is R2, which is 200 plus minus 2 ohm, are connected in parallel. So they are connected in parallel. Resistance of this parallel combination is going to be what? So let's see solution, and along with this solution we will be forming a formula. We know in case of parallel combination, we know equivalent resistance or net resistance, that is, let's say net resistance is R. So we write 1 upon R is equal to 1 upon R1 plus 1 upon R2. Now we know the value of R1, 100 is the value of R1, 200 is the value of R2. We can substitute over here. So it's going to be 1 upon 100 plus 1 upon 200. If we simplify this, so we multiply by 2, 2 plus 1, that becomes 3, 3 divided by 200. Then we will be making it upside down to get the value of R. So R value is going to be 200 divided by 3, which basically will become 66.66. And you can write this up to whatever the number you want. So this is 66.66, and further 6 if you can write. I'm writing just the calculated value, then we'll be putting it to the appropriate number of significant figures. So this is going to be the R value. Up to this there is a no big deal, because this is the only formula that you need to know. You might be knowing from your 10th standard. Okay, now onwards, the point is when we are going to rewrite this, or we want to find the error out of it. So what should be the formula for error? Now you see this expression that is given over here, it is not matching with this the old ones. Earlier we have talked about for addition, subtraction, multiplication, division and power, and this is neither of them. What it is doing, it is making the reciprocal, then addition. So here if you remember the procedure, taking logarithm function, then segregating, that won't work. So what is going to work over here is differentiation. So we will be differentiating both sides, simplifying and finding out the final expression. So in this kind of expression, what the final error expression comes out to be, that I'm writing over here. After doing this, you are going to get it as a delta R divided by R square is equal to delta R1 divided by R1 square plus delta R2 divided by R2 square. So for the time being, you just learn this. For this kind of expression, whenever you are having 1 upon something is equal to 1 upon something plus another thing, so this will have an error formula like this. So the denominator becomes square, and in numerator error comes in. So error of this R divided by this R square. Similarly, error of this R1 divided by R1 square plus error of R2 upon R2 square. How it is coming, there is a mathematics involved called differentiation. In the next chapter we will be talking about the differentiation, then you can easily understand how it is coming. For the time being, you can remember as a formula. So you can note down this as a formula, and whenever this kind of parallel combination is coming, you find delta R using this. If you are using anything else, that's going to be wrong. Okay, now we can find out what the delta R is going to be. So we say delta R divided by R square. R we have already calculated, so that's going to be delta, or we can rewrite it as in this way. Delta R is equal to, we can write it as R divided by R1 square, or you can say whole square of this number, into delta R1, that's a delta, plus R divided by R2 whole square into delta R2. Now you know all the values, like delta R1. What is a delta R1? That's a 1. What is delta R2? That's a 2. And what is R? R is 200 by 3. And what is R1? That's 100. And this R2, that's a 200. So we can put all the values. So let's put the values and try to find what this delta R is going to be. So delta R will be equal to R, that is 200 divided by 3, into R1, which is 100, square of this number, into delta R1, which is 1, plus again r, which is 200 divided by 3, into r2, which is 200, square of this number, into delta r2, which is 2. Can you see what I'm writing? I'm writing from this these given quantities. Then you can say this can be simplified. So first term will become 4 by 3, sorry, 2 by 3 square. So 2 by 3 square is 4 by 9, plus, if you simplify this, it's going to be 2 by 9, 2 by 9. We can simplify this to become 6 by 9, which can be further simplified as 2 by 3. If we are making it as 2 by 3, so that's going to be equal to 0.666 ohm. So that's going to be the value of delta R. Now let's come to those rules that we can use. The number of significant figures in delta R has to be same as the significant figures in R1 and R2's error. R1 error is 1, R2 error is 2, so they have one significant figure, so delta R must be up to one significant figure. Hence, this delta R can be written as, so let me use the different color. Delta R appropriately is going to be equal to having one significant figure, so that means this has to be rounded off, and this is 6, so that can be made as 7. So this becomes 0.7 ohm. So 0.7 ohm is delta R. Now, if it is delta R has been calculated, so we can also talk about what the R has to be written as. R is this number, so it has to have a same number of decimal places as this delta R. So it's a one decimal place, so we can convert it up to one decimal place. So we will be getting it as a 66.7 ohm. So final answer will become, or our answer will become, R plus minus delta R. So this has to be written as 66.7 plus minus 0.7 ohm. And then we can check which option matches perfectly. So if you go for the first, that's not appropriate. If you go to the second, that's also not appropriate. Third, not appropriate. Fourth, that fourth is matching. So we will say D is our answer. Making sense? I hope it's making sense. So this was an important example, and particularly this important expression you have got. So remember this expression. Whenever this kind of equation or relation is given to us, we can find out the error by using this. And if you remember this, then calculation is going to be easy. We are following certain rules that we have learned in this video lecture and the prior to this lecture. Okay, so these were few questions that we dealt with. Go through them, make your notes and note down the important points, and if you got any question or confusion, you just ask. So before we conclude this, I'm giving you one question. You solve that and give the answer in the comment box. So here's the question that has to be tried by yourself, and I'm hopeful if you have understood this video and the prior to this, you will be able to answer. It says if the error in the measurement of volume of a sphere is given to us, we need to find the error in measurement of the surface area. Options are given to us, so you solve and answer in the comment box. Okay, well, so that's all for this video. Thank you for watching. Have a great time.